probability here. And so what this thing says is this is a function that maps verb to the best length k sequence that ends in verb. Okay, and the definition, the mathematical definition is simply, well, I do an argmax over all sequences of length k minus 1. I append verb to it, compute the probability, and take the one that has the maximum.
Given the words that
Yeah, so we're given x, we want to predict y. So this is an intermediate step. We're given the first k x's. I want to predict the best length k sequence of y's that ends in verb. Similarly, I want to predict the best length k sequence of y's that end in noun. And mathematically what that means is I look at all possible sequences of part-of-speech tags of length k minus 1, append a noun to the end of it, measure the probability, and take the one that has maximal probability. So if I assume that I've already have these solutions pre-computed, right, in my iterative algorithm, and the claim is that it's easy to compute these solutions for the k plus 1 step. And so for the k plus 1 step, the claim is that I want to solve this. If I've already pre-computed these for all part-of-speech tags for all length k part-of-speech tags that end in each part-of-speech tag, the claim is that I can easily compute this for length k plus 1. And if you look at the definition of the k plus 1, because of the first order dynamics, right? Because of the first order dynamics, you could write the probability of this guy as the probability of the probability of the first k times the transition probability times the emission probability of part-of-speech tag to words, right? This is just a Markovian decomposition of the definition. And this guy, we've already pre-computed. Right? So we don't need to know the sequence, the entire sequence. We know that the best possible sequence, we don't have to iterate over all L to the k possible subsequences of length k. We know that the best possible sequence that ends in noun is this guy. Sorry, this guy. We know that the best possible sequence of length k that ends in verb is this guy. So the number of sequences we need to iterate over is of length, the number of tag, is equal to the number of part-of-speech tags. So we don't need to iterate over all possible part-of-speech sequences of length k. We just need to iterate over these 6, and then figure out which one transitions to the next. Yeah.
So this takes L times n time now, or
L squared. So if you want to compute this for all possible if you want to compute this for all possible part-of-speech tags, then you iterate over. This is L. This is L. This takes length L. You want to do this for all possible part-of-speech tags, it's L squared. And you do this for up to length m, so it's L squared times m. So I have an operational example in this slide, so maybe that'll clear things up. So here's the operational example. So at time step 1, so for k equals 1, we have to store the best length 1 subsequence that ends in verb, determiner, noun. I'm just going to use these 3 part-of-speech tags for simplicity. In the base case, so this is the way you prove that this is correct is using induction. But in the base case, which this is the base case. This is just simply the best length 1 sequence that ends in verb is just verb, right? The best length 1 sequence that ends in noun is just noun. The best length 1 sequence that ends in determiner is just determiner. So this is trivial, right? So now here's the inductive case. So here's where it gets interesting. So we assume that we've already pre-computed the best length k minus 1 subsequence, length 1 subsequence. Now we want to solve for the best length 2 subsequence that ends in verb, that ends in determiner, and ends in noun. So let's look at this one first, right? So we say, okay, what is the best length 2 sequence that ends in verb? Well, it's either the best length 1 sequence that ends in verb, and then multiplying that probability by the probability of transitioning to verb and emitting the word in the second token, or it's the best length 1 sequence that ends in determiner, multiply that probability by the transition from determiner to verb, and multiply by the probability of this verb, of verb emitting whatever word is in the second token. Or it's the probability of the best length of one subsequence that ends in noun, and having noun multiply the probability of noun transitioning to verb, and so on and so forth. And so we just loop over these three possibilities, take the one that has the highest probability, and that's it. So let's say for simplicity we did that, and it was noun to verb, right? What this means is that we no longer need to remember these two solutions, subsequences, because their probabilities are dominated by the probability of this subsequence. Okay, so now what that means is that y2 of verb is the sequence noun verb. So now we can do the same thing for the y2 sequence of determiner. We looked at the transition from verb to determiner. We look at the probability of this guy times the transition probability. The probability of this guy times transition probability. Probability of this guy times transition probability. We choose the one that has the highest one, and we do the same for all possible part of speech tags of sequences of length 2 that end in each part of speech tag. So now there are only three sequences we're storing. We've thrown away all the other subsequences. There are only three subsequences of length 2 that we're storing. There's 9 total possibilities, but we've thrown away all but 3 of them. Yeah?
So the fact that you can only store the best sequence of length k minus 1, that's first order dependence.
Yes, because of the first order dependence, it's like, it takes a lot to internalize this slide, but once you do it because the notation is a little, I made a notation heavy just for the sake of completeness, so it takes a little while to internalize the slide. But basically the first order dependence says that the probability of this probability factorizes into the probability of this length k plus 1 subsequence factorizes into the probability of the first length k times the first order transition times the emission probability. And therefore, if I already solved for the argmax of this guy, right, then I don't need to repeat all the work that I did. Does that make sense? Mm-hmm. Yeah.
So when you get to higher orders, like, do you just have, like, for example, for like a second order?
You have to keep track of the previous 2.
Okay.
So for a second order, you'd have to keep track of all best length k prefix sequences that end in verb, that end in verb noun, determiner noun. So then it's L cubed times n, not L squared. And for arbitrary order, you're back to exponential. This process continues iteratively. At every step in this iteration, we make the inductive hypothesis is that we've optimally solved for the best length k subsequence that ends in each part of speech tag. And given that, we can efficiently compute the best length k plus 1 subsequence that ends in each part of speech tag by only looking at the solutions here, multiplying the probabilities of these by the transition probabilities, and picking the one that has the maximum. And again, if you feel you want to review this again, there's a recitation tonight that goes over this again. So here's why this works. I mean, intuitively, I've already explained it, but we want to prove that this works. Right? Suppose that y, let's see, what did I write here? Right, okay. Suppose that, here's the solution for y. Suppose that y2 of v is noun. Y2 of v is noun verb, right? So y3 of v cannot. If y3 of v, so the best length 3 subsequence that ends in verb, it cannot be verb, because the best length 2 subsequence is not verb, it's noun verb, right? So here's how I can prove that this algorithm is correct is you just do a proof by contradiction. Suppose your algorithm, if you did exhaustive search, gave you this. You just prove that whatever probability this has, this would have higher probability, which is the partial solution returned by the best length 2 subsequence. and it just depends on the first order property, right? The probability of this sequence and this sequence differ in 3 terms, right? It differs in this term, and this term. None of these 3 terms depend on Y3. That's the first order property. That's the memoryless property. If you look at the probability distribution of a hidden Markov model, the probability difference of these 2 subsequences only differ in these 3 terms, none of which depends on Y3. And this argument, of course, generalizes to arbitrary length. I'm just showing you for length 3. And that's how I can prove that this algorithm is correct. Any questions? By the way, you have to implement this for the homework. It's a lot of fun once you get it working. Okay, so just a recap of the Viterbi algorithm. By Bayes' rule, we solve this by solving this. We can ignore the p of x because it's constant over all possible y's, so we're just doing argmax. And then, so basically for k from 1 to m, iteratively solve this problem as defined by the formula in the previous slide for every possible part of speech tag. And then at the very end, after you solve this problem for up to length m, you pick the y of m of z, you pick the part of speech tag that has the highest total probability. And this is the Viterbi algorithm. It's an instance of dynamic programming. How many of you have learned about dynamic programming already? Okay, and how many of you have not? Okay. Well, there is a recitation tonight that recaps everything that I'll be talking about here. That hopefully, if you just hear it twice, you can internalize better. Okay, so here's a numerical example. Fish sleep. So this is the verb. This is the part of speech tag transition probability. Transition probabilities. So here's another, just another version of an operational example. So we start with in the start state, and then the first token is fish. So we consider the transition probability from start to verb, the transition probability from start to noun. We store that, right? Oops. We store that. And then for the second verb, sleep, we consider the probability of a transition from verb to verb, from noun to verb, and then we compute this guy. Sorry. And then we consider the probability of transitioning from verb to noun, noun to noun, and we multiply all the probabilities together, and we consider this, we take this guy. So the best length to subsequence that ends in verb is verb verb. The best length to subsequence that ends in noun is verb noun in this particular example. Oh, sorry. I confused myself. Sorry, this is iterating over every possibility. And then we take the best one. And then after this, we make a prediction of, if you include the end state, we do the same thing for the end state with the transition probabilities. And then that's how you get your answer. And so notice that we did not, consider all possibilities. So what might go wrong for super long sequences in this computation? Does anyone see the problem?
Numbers will be very small computer assumes they're 0.
Exactly. The numbers are extremely small because they get repeatedly multiplied by values that are less than 1. So you're going to underflow very, very, very quickly. And so if you don't account for this in your homework, that might happen in the homework as well. So there's a simple trick to dealing with this. Instead of multiplying numbers, you just add their logarithms. So you operate in log space. Right? So you iteratively solve for this in log space. You keep the probabilities. Sorry, I'm abusing notation here, right? I'm saying this gives you the best subsequence, but you also have to keep track of the probability, right? And I'm just saying keep track of the best sequence and the log of the probability. And the nice thing about log of the probability is that it's additive, right? So now you're not going to underflow. Yeah.
So
doing dynamic programming, you would have like after every step just like normalize your function and keep doing that so that the numbers can get smaller. Because once you complete like the last one, we should make the next optimization step, you can just like scale them up, right? Doesn't matter.
Let me think. So there are definitely variants of dynamic programming where you can do that, and that's correct. For Turby, my only concern is that suppose we had a super long sequence and then this number was like 0.9999999 to 0.000001, and then you renormalize. If you renormalize, eventually this goes 1 to 0, right?
Okay, so within one step, they're all
Yeah, within, like you can imagine if you keep normalizing, like if you have a super long sequence, within the first sequence, one of them just goes down to almost 0, and then through the first half of the sequence, and then in the second half of the sequence, it goes back from almost 0 to much higher, right? You could recover the probabilities if the prediction task is long enough. But you underflowed in the first half of the sequence, and now it's zeroed out, in which case you're screwed.
So you're underflowing in both directions, like along the steps, it decreases.
There are definitely
also within the steps.
Yeah, there are definitely instances of dynamic programming problems and where normalizing works and is what you should do. There are also versions of dynamic programming like this one where you should take the log of the probabilities. Right? It doesn't really affect the correctness of dynamic programming. It's just a way of adjusting for overflow/underflow. Right. Okay, so just to recap, independent classification treats every word completely independently, and you make mistakes due to not modeling context. HMMs deal with this, and how you can do efficient prediction using in HMM is via the Viterbi algorithm. Okay, in the final 30 minutes or so, I'm going to talk about training HMMs, unless there are any questions on Viterbi. Okay, let's talk about training HMMs. Okay, first let's consider supervised training. So what you're given is a training set of x, y pairs. Here x is a word sequence, and y you can think of as a part of speech tag sequence, although I'm going to treat them pretty generically. So the goal is to learn a model of the joint distribution, right? And again, we're going to do it using the principle of maximum likelihood. So simply choose the parameterization of this probability function that maximizes its probability on the training set. Just an aside on the matrix formulation, I alluded to this in the naive Bayes lecture. You can also represent things in matrix notation, like people often call the transition matrix from one y to the next y as A, and they often call the observation matrix, which is the word you see given the word x you see given a y, as the observation matrix. Just some terminology. The reason why you might want to use this notation is, well, it's a lot simpler, right? In the dynamic programming, in the Viterbi algorithm, I had this probability of blah, 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 and it's this huge notation. You could simply, if you use matrix notation, it says an entry of this matrix entry. So it's, this is just mathematically just more concise, and once you internalize, become comfortable, reason about things in terms of these matrices, everything just looks simpler. Okay, here's the principle of maximum likelihood. So given some training set, I want to maximize the probability of my model generating this training set, assume the training set was sampled independently from the test distribution, right? And the definition of this guy is equal to this guy by the formula in Markov models, and then via the same derivations that I showed you for naive Bayes. Hidden Markov models have the same type of independent structure as naive Bayes. So you can just actually estimate this via counting. The maximum likelihood solution is counting, right? So what is the probability that given that your current token is, your current y is b, for some b, what is the probability of transitioning to the next y being a? That's the A matrix in cell A, B, little a, little b. And simply the frequency by which that happens, divided by the number of times that happens in your training set, divided by the number of times that you observe the token b, y equals b in your training set, across all tokens, across all sequences in your training set. What is the probability that given that your current token is z, that the word you see associated with that token is the word w? Well, it's simply the number of times you observe the WZ pair in any token in any sequence in your training set, divided by the number of times you observe the token Z in your training set. This is just a strict generalization of how you do maximum likelihood estimation for naive Bayes. And you could derive it by minimizing the negative log likelihood derivation, just like I showed you in the previous lecture. So this is a supervised case. Let's see. Oh, I already went over this. So I actually already went over this. So the reason why, so I guess even this is a strict generalization of naive Bayes. The reason why the reason why the counting works is because the only thing that's different is this thing that you need to count. Everything else is basically naive Bayes, and this you can count because it's conditioned because of the condition dependence assumptions. So what I mean by this is, I told you that a single token y generates token x. You can think of it as naive Bayes. You can also think of the previous token y generating the next token y is also like a little piece of naive Bayes, right? And so if you take that interpretation, then it's just that's how you get the counting argument. And if you do the negative log likelihood derivation, just like in the last lecture, then you also get the same solution. So the number of parameters is the number of tags squared plus the number of words times the number of tags. Right. So typically the number of tags, is in the dozens. The number of words, maybe 10,000, maybe 1 million. And so the reason why people like models like linear Markov models, at least traditionally, is because it's a fairly compact representation of sequences, because the square transition probability matrix is on the tags, right, and not on the words. Okay. Yeah.
What happens when you get a word that you haven't seen before? You
haven't ever seen before?
Like in any of your training?
You get 0 probability unless you do regularization. So regularization, so you could add pseudo counts here, just like in naive Bayes. Right? If you don't regularize and you see a word that you've never seen before in your training set, you just get 0 probability. Like the model will just crap out if you try to do inference on it. But if you do regularization, then it'll assign a small probability to it, even though it's never seen it before, right, with pseudo counts. Okay, so that was supervised training. What about unsupervised training? Sometimes we don't have the part-of-speech tag. Sometimes we just have the words, the sentences, right? What happens if we don't have the Ys? Well, okay, let's say we still want to estimate the maximum likelihood solution, right? The maximum likelihood solution is, since we don't observe the Ys, we want to maximize the likelihood of the X's according to our model. And this is just a marginalization out of the Ys. So we want to find a maximum likelihood of our probability little tables that define the hidden Markov model that maximizes this probability. How do we do that? Why do we want to do that? I think why is easier to answer than how. So let me answer the why first. So this is an instance of unsupervised training, which I'll talk about in greater depth in the second half of this course. The reason why I want to do unsupervised training is, well, you know, supervised data is hard to acquire, right? Some human person had to annotate a sentence with part of speech tags. That is not cheap, especially if you're talking about large data sets, right? Whereas supervised data is inherently expensive because of that. Unsupervised data is plentiful. Just download all the text on the internet. Right? So if we have the right way to train the hidden Markov model in the unsupervised way, it just might work for something like part of speech tag. And certainly there is sort of the thing that's between unsupervised and supervised, which is called semi-supervised, where you have some part of speech tags, a small amount, and then a huge amount of unlabeled data. Right? How do you combine both to train the most accurate model possible? Furthermore, you know, as I talked about towards the end of the previous lecture, models like topic modeling and all these other modeling approaches, probabilistic modeling approaches, those are typically trained, not always, but usually trained in an unsupervised way. And what does that mean? That means that they're trying to learn a set of sufficient statistics that summarizes this data. Not necessarily to try to make a prediction, but just to summarize it. And those can be used for various things, like in the, the analysis of Sarah Palin's emails, where the sufficient statistics are that there's only a small number of topics. All the words you see must be coherently amongst a small number of topics. You can also say, I want to detect sentences that seem very strange, right? Usually people don't say a sentence that looks like this, right? So you could do outlier detection if you have a probabilistic model that says, okay, here's a sentence that has very low probability according to my model on this unsupervised training set. So maybe there's something strange about it. And again, we'll talk about unsupervised learning in greater depth in the second half of this course. Okay, so the most common way to estimate these types of models, oh yeah, by the way, I should mention that this is why it's called a hidden Markov model. In most cases where people think about HMMs, or I don't know about most, but in many cases when people think about HMMs, certainly in the early cases, it's assumed that the Ys are not observed, at least most of the time in the training set. So the Ys were hidden, hence hidden Markov model. It's a model with Markovian assumptions, first order Markovian assumptions, where the Ys are, for the most part, hidden in the training set. Okay, so the way that we would typically estimate parameters for hidden Markov models and any other model with hidden variables at training time is using the EnAlgo, which stands for expectation maximization, also known as Baum-Welch in the hidden Markov model literature. So here's the intuition. If we had the Ys, training the parameters are easy. We just do maximum likelihood. Simple, right? If we had the models, we can predict the Ys. If we had one or the other, it would be done, right? So, but we have neither. So it's a chicken and egg problem. So the EM algorithm basically says, let's just randomly initialize our model. We can use that to sort of predict a bunch of Ys for each training sequence X. This is called the expectation step. Given these Ys, let's estimate a new model. This is called the maximization step. And let's repeat until we converge and hope that it's a good model. So we break the chicken egg cycle by random initialization. So the expectation part is fairly straightforward. It's just maximum likelihood. So we're given our model parameters, the transition matrix from tag and the observation matrix from tag to word. And we're given training examples of this form, that's all we get. And now we want to predict the distribution over the tags. Want to predict the distribution over the tags. So it encodes the probability, so that something that looks like this, right? This is what we want to predict given this x. That should be an m. So I apologize. And you can think of this as the marginal distribution of each y. So So we're predicting the probability of each y, each token in the sequence, while not considering, while marginalizing out the probabilities of the other y's in this sequence. And you get a table that looks like this. Just a recap of the matrix formulation. And yeah, by the way, I'll tell you how we do this in the very end. But let's say we have that already. So recall that this is the maximum likelihood estimate in the supervised case, right? We just simply do a count of the number of times we observe this token, this transition, divided by the number of times we observe this state in any sequence, in any token in any sequence. For the observation matrix probabilities, we count the number of times we observe this part-of-speech tag word pair divided by the number of times we observe this part-of-speech tag, right? In the unsupervised case, we don't have we don't observe the y's, but if we had a previous A and O model, we can predict these marginals, which I assume that we can. And then you just estimate the new quantity using these probabilities. So if you were able to compute these guys, then estimating new model parameters is just a smooth version of the previous formula. So this is very straightforward. Now, the last step is how to compute these. And this is called the forward backward algorithm. It's also a dynamic programming approach, similar to Viterbi, but a little bit different. It's a little bit of notation. And again, this will be covered in recitation again tonight. So if you want to just see this being presented just another time, you can come to recitation tonight. So let alpha sub z of I denote the probability of the ith token being z, given our current model in our EM steps. We've estimated an intermediate model and want to compute the marginal distribution. So let alpha be the prefix probability of y sub I equals z given the first I subsequence of the input sentence, excuse me. And let beta sub z of I be the suffix, right? So given, we want to predict the probability of the final I plus 1 to m subsequence of words, given y sub I equal to z and our model. You can show just through arithmetic that the marginal probability of y sub I equal to z given x is equal to this ratio. And here, you have to normalize, otherwise you'll underflow. So the forward backward algorithm basically says, I want to be able to efficiently compute